Good afternoon, sir. Today, me and my group members are here to present alpha beta pruning, which we have applied on the game of checkers. The game of checkers is considered a complicated game with 10 raised to the power 20 possible legal positions in English draughts version, that is 8 cross 8 board alone. For our project, we decided to implement a game playing artificial intelligence agent. We chose this because it was a very concrete topic covered and because it would be an interesting project that we would be able to play in future and share with others also. Our approach is to create a computer based agent on Minimax algorithm together with possible improvements, which is state of art in one on one game. Furthermore, we chose to implement the entire game and AI scratch using Python. For this reason, we decided to forego making the game look aesthetically pleasing in the favor of focusing on the functionality of the game and more importantly, the functionality of the AI. Visually keeping track of the board was not much a challenge since we just needed to write a method that prints out data stored in our grid in the manner that makes sense.
Now let's talk about the checkers, rules, and gameplay. Game pieces and board. Checker is a board game played between two people on a 8 by 8 checkerboard like the one shown below. Each player has 12 pieces that are like flat round discs that fits inside each of the boxes on the board. The pieces are placed on every other dark squares and then staggered by row, like shown on the board. Each checker player has different color pieces. Sometimes the pieces are black and red or red and white. Now let's talk about taking a turn. Typically, the darker piece moves first. Each player takes their turn by moving a piece. Pieces are always moved diagonally and can be moved in the following ways. The first, diagonally in the upward direction to the next dark square. Second, if there is one of the opponent pieces next to a piece and an empty space on the other side, you can jump your opponent and remove their pieces. You can do multiple jumps if they are lined up in the forward direction. Now let's talk about king pieces. The last row is called the king row. If you get a piece across the board to the opponent's king row, that piece becomes a king. Another piece is placed onto that piece so it is now two pieces high. King piece can move in both direction, forward and backward. Now let's talk about winning the game. You can win the game when the opponent has no more pieces or can't move. If neither player can move, then it is a draw or a tie.
This is the checkers game that we have made. I just have to run the main.py file. The red pieces are played by me and the white pieces are played by the AI. If I click on any red piece, I can see the blue dot starts appearing. The blue dot represents the valid moves for that piece. As soon as I play any move, the AI move instantaneously, and we can see the time taken by AI to do that also in the terminal, like that. If a piece reaches towards the end, and this is the double jump, I think. Mhm. Yeah, so this is a double jump example. There is a piece I can skip over, and then there is another piece I can skip over. I can do it in a single move also. If piece reaches towards the end, it will become the king piece, and the king piece can move in both forward and upward direction. So this is the gameplay. Now I will compare with only min-max version of the checkers. This is the check only min max. Terminal is visible. No. Mm. First, I will check with alphabet running. We can see the timetable on the terminal. Now with min-max, with only min-max. As we can see, the time taken is significantly longer than alpha beta pruning one. Now we will discuss the code part. So we have this checkers library file. In this we have the piece.py file. If we have the piece object, then this piece object will have the rows and the column which is currently color of the piece, and if the piece is a king or not. This calculate position will calculate the position on the board which the piece should have. So we can see it like that. This will make the piece a king when it reaches to the end. If the piece is become a king, then we have to piece become a king, then we have to put an image of the crown on it, and this function for moving the piece. And we have just update the rows and columns. And this is the board.py file. The draw square function will draw the checkered pattern of the board, the red black. The evaluate function will evaluate the score for the min-max algorithm. This will get all the pieces. This function self-explanatory. And this function will move the pieces on the board, and if any piece will reach to the end, we will make that piece a king piece, and we will count. We will increment the counter. And this putting the piece for, and this is for the create board function. We first start the program. We can see from row 0 to row 3rd we have right pieces, from row 5 to 7 we have red pieces, and there is no pieces in the 3rd, 4th and 5th row. Sorry, 3rd and 4th row. This is all update. Update. This is the board, the draw function for drawing the pieces. The draw function is for drawing the pieces on the board. Once we move it, This is for removing the pieces, for checking the winner, and this is the main function, important option for identifying the valid moves of the pieces. First we have the move. This is the dictionary for all the valid moves. Like if the piece is red, the red pieces are move in the negative direction, the white pieces in positive direction, and the king piece move can in both upward and downward direction. So first we have traverse left function and the traverse right. I will explain one function. So first we initialize the moves dictionary. Maybe in the last, this is the last position which we have traversed. So what it will do, first it will check the diagonal pieces. It will go left and check the diagonal pieces. If there is an empty, for example, this is current is equal, now current is equal to empty. If the pieces, we have not skipped any pieces, so we will go into the else condition. That means we will store the last position, and as you can see the last we have passes left, so this is the valid move and we will store in the moves dictionary. So this will happen when this condition arises when we have skipped the pieces and there is no other way to move, so we will break out of the move, and when we skip the push we can double jump pieces, and last we will, like if we have moved last we will check for any double jumps and multiple jumps. Yes, this is condition for if we have this our piece in blocking our way, so we will break out of the loop. Else after all of that we will last equal to current for storing the last value, last position, and every time this will happen we will decrement left by 1 so that it will move in only diagonal direction, and we will return move dictionary, and this is the same for the traverse right function also. So this game, this is the constant file. We will also store the dimension, the color, images, max value. This is the game.py file. This is for updating the pygame window. Every time we move the piece, we will draw the piece, we will draw the value piece, and then we will update the wizard window. This is for checking all the winner. And this is for selecting the piece when moving the piece. And this is for drawing the valid moves on the this blue dots for drawing. This function is drawing that valid moves. And this function for changing the turn, and this for getting the board, and this for AI. After every time we have to change, after AI has moved, then we have to change the turn. Now comes the algorithm part. In this algorithm, like in this mimics with uprouting pruning, we have 5 parameters: position, depth, max player, and game alpha beta. If the position is the move, the depth is the depth of this tree, how much moves ahead the algorithm has to think. Then the max player, there is a boolean value, we have to change it every time. The first determining condition, if depth equal to 0 or position is none, then we will return the position score, the position. This max play count. This max play we will initialize max evaluation is negative infinity, best play is none. Like we will trace all the moves and we will evaluate through the min max function. We will pass the current move depth -1. We will change it like max value to false. So the next time it will run the min value. Again the alpha beta. We will check what is the maximum evaluation, and then this will check like alpha yes, maximum value alpha 2, and this is the maximum value of alpha. If a maximum evaluation is equal to evaluation, then this is the best move, then we will store in the best move. For terminating the unnecessary moves, we will write beta is less than equal to alpha, then we will break out of the loop. This is same for the min values also. So the function will take the get all moves. So this is for getting all the possible moves on the board from that position. And this is for simulating the moves. And this is for drawing over the green circles. If we uncomment this line, we can see the algorithm visualizing it. We have to number 5. In this slide, you can see how the algorithm is step by step evaluating all the positions. Then comes the main.py file in which we have imported our checkers that and we have imported our checkers file with the min-max algorithm. We have set that setting is 260 for the 5-in window, and this is the window. We have set the height and width in the constant. We can change that also. This function for getting the mouse position, if run is true, we will get the time pulse of the clock, and we will initialize the game object. First we will start with the white game with the game tone is white, and the min-max algorithm will be run. Start and end time for calculating the time taken. In this game, AI move will update our board and change the turn. This is for evaluating if there is a winner. And this is for getting the position of the mouse. By that we can select on the with this, like we can select the pieces on our board.
Further improvements and conclusion. While this does give an answer to our initial question of what would be the best heuristic function to use for the checkers, the answer may possibly be further improved. A major improvement that can be made on our strategy of determining the best heuristics would be to increase our resources. Our biggest limitation would be the lack of resources we faced when we were testing the heuristics. The heuristic value for the opponent could potentially be improved by looping through more specific numbers rather than the larger integers we used. Example, iterating over 0.1 rather than 3. Also, it has been stated we primarily tested our heuristic on other AI. An improvement could also be made if a sort of beta testing would be used, in which we used a different heuristic to play against many human players to see if humans behave like AI or if there are any different factors need to be considered. So we are very confident that our heuristic function of our checkers play artificial intelligence can be more than hold its own, that further improvements can be made providing the right resources.